Welcome to another module in this massive open online course on Bayesian MMSE estimation for wireless communications. Alright. So now, so far in the previous modules, we have looked at an application, we have looked at MMSE estimation when both the observation and the parameter is distributed as Gaussian random variables, and we also looked at an application of the MMSE estimator for a wireless sensor network. Let us now look at an MMSE estimation example for wireless channel estimation. So we want to look like, so today we would like to look at, or we would like to look at wireless channel estimation, or more specifically an application of MMSE. So, MMSE, which stands for minimum mean squared error, channel estimation. Okay. So, this is what we would like to look at. Now, let us start by considering a wireless communication scenario. Consider a wireless communication okay. In a wireless communication scenario, what do we have? We typically have a base station which is transmitting to a mobile terminal or a mobile device basically, right. So, let us consider this scenario. Let us schematically represent this scenario where I have a base station, right. I have this base station which is transmitting to a mobile. Okay. So, I have a base station with an antenna which is transmitting. So, what is this? This is my base station. Which is transmitting to the mobile or wireless device, your mobile device, okay, over the radio channel. Okay. Now, let us say the transmitted symbol is denoted by xk, the received symbol is denoted by yk. Okay. So, we have a transmitted symbol which is denoted, the kth transmitted, k denotes the time instant. So, xk is the transmitted symbol, the received symbol at your mobile device is yk, this is your received symbol, and we have a channel h, this is basically denotes the channel coefficient, the wireless channel coefficient. So, xk is a transmitted symbol that travels through the channel, or that basically traverses this radio channel, characterized by this channel coefficient h, and the corresponding received symbol is given by yk. Therefore, this system, this input output model, where the input is the transmitted symbol and the output is the received symbol, can be modeled as, so wireless MMSE, for wireless MMSE channel estimation, we have the model given as yk equals h times xk plus vk, where yk is the kth received symbol, correct. This is the kth received symbol at the mobile. Okay. We are considering a simple downlink scenario, although this can also be an uplink scenario. Okay. So, this is a kth received symbol. H is the unknown fading channel coefficient which has to be estimated. This is the unknown, that is the important point. This channel coefficient is unknown, is the unknown fading channel coefficient xk is the transmitted pilot symbol. This is the transmitted pilot symbol. I am going to talk more about this shortly. So, this is the kth transmitted pilot symbol and Vk is the additive white Gaussian noise. So, Vk, this is additive white Gaussian noise, this has mean equal to 0, the mean of the Gaussian noise is 0, variance equal to sigma square. So, the mean of this Vk, which is the additive white Gaussian noise, the mean is 0 and variance is sigma square. And the key aspect here, the important part here is that this channel coefficient h, this is the channel coefficient h which is unknown, and estimation of h is termed as channel estimation. Estimation of this unknown channel coefficient h, estimation of unknown channel coefficient h is termed as, this is termed as channel estimation. This is termed as channel estimation. Okay. And for this purpose of channel estimation, the base station transmits a set or a sequence of pilot symbols. All right. There are two kinds of transmitted symbols. One is the information symbols. These are unknown to the mobile, all right, because these carry the information. However, the transmitted pilot symbols, which do not carry any information and are simply used for channel estimation, these are a fixed number of or a fixed sequence of pilot symbols which are transmitted by the base station, all right, to aid the mobile or to help the mobile perform channel estimation. So, base station transmits a set of n pilot symbols for channel estimation. It transmits a set of n pilot symbols for channel estimation, and these channel pilot symbols we are denoting by x1, x2, so on up to xn. These are the n pilot symbols transmitted for the purpose of channel estimation. All right. So, the model that we have for channel estimation is the following. All right, we have y1, that is the first received symbol corresponding to k equal to 1 equals h times x1 plus v1, okay. y2 equals h times x2 plus v2, so on and so forth. Yn equals h times xn plus vn. Okay. So, this is the model. Okay. So, we have n received symbols and this is basically the model. So, we have n received symbols corresponding to the n transmitted pilot symbols, and V1, V2 up to Vn are the n noise samples. And what we are going to do now is basically we are going to vectorize this model, that is represent this model using vector notation, okay, and that will be convenient for manipulation. So, that will be convenient to later manipulate it to a form that is and get the final expression for the channel estimate h. Okay. So, now what we are going to do is we are going to recast this as the vector model going to recast this as a vector model. First we can write the received vector y bar, okay, that will simply consist of the received symbols y1, y2 up to, okay. So, we have the received vector y bar which will consist of the received symbols y1, y2, yn, which is basically the channel vector, which is the transmitted symbol of vector of pilot symbols x1, x2 up to xn times h bar plus v1, v2 up to vn. This is the noise vector. So, what we have? We have y bar which is the received vector or observation vector, okay. We have x bar which is the pilot vector, and we have v bar which is the simply the noise vector, and therefore, what we have is we have y bar equals x bar times h plus v bar, all right, and h is the unknown channel coefficient, and each vector y bar, h bar and v bar are of size n cross 1. So, these are n cross 1 vectors, h is the unknown channel coefficient, and this is our model for channel estimation. And one more assumption, remember we already made this, we are going to assume that these noise samples V1, V2, Vn are IID Gaussian. IID Gaussian means independent identically distributed Gaussian. Similar to the wireless sensor network, these each has mean 0, variance sigma square, and they are independent. Independent means, so V bar, V1, V2, Vn, these are independent. Just to briefly repeat this, V1, V2 up to Vn, these are IID Gaussian, means each has mean 0, variance sigma square, and they are independent means that expected value of Vk into Vl, two different noise samples Vk into Vl is equal to 0. That is, this is equal to, this can be simplified as if k is not equal to L, this is expected value of Vk into expected value of Vl, and since both these expected values are 0, this can be simplified as equal to 0 if k is not equal to L, all right. Therefore, the covariance, and this is also something that we have again derived in the context of the previous example for the wireless sensor network, that is expected V bar transpose is sigma square times identity matrix. This is the covariance matrix. Covariance matrix of your noise vector, covariance matrix of the noise vector V bar. Further, we are going to assume similar to the previous MMSE estimation framework, because remember for the MMSE, in the MMSE estimation scenario, the parameter h is considered to be a random parameter. That parameter h is considered to be a random in nature, all right. And similar to the MMSE, since this is, we are considering the Gaussian MMSE estimation framework, we are going to assume the channel coefficient h to be Gaussian in nature, all right. We are going to assume the channel coefficient h to be Gaussian in nature. In fact, this is a very valid assumption, because for a practical wireless scenario, the channel coefficient h is considered to be a complex Gaussian channel coefficient. This is also known as a Rayleigh fading channel coefficient, that is a symmetric complex Gaussian channel coefficient h, which is also known as a Rayleigh fading channel coefficient, because its amplitude follows the Rayleigh probability density function, all right. For the purpose of illustration, however, we are going to simply consider a real channel coefficient h in this discussion. However, it can be very easily extended to a scenario where the channel coefficient h is complex in nature, okay. So, our assumption here is basically that this channel coefficient h is Gaussian with mean, that is expected value of h equal to mu h, and variance, all right, and variance expected value of h square equal to sigma h square. We are going to consider this at present to be real in nature, but we will also note that it can be extended to a scenario with complex channel coefficient h. This can be easily extended to a scenario with complex channel with a complex channel coefficient h. Okay. And therefore, we have assumed something about the channel coefficient. We have assumed that the noise vector to be, the noise samples to be IID, independent identically distributed Gaussian with mean 0, variance sigma square. Okay. These are the two assumptions that we have, fine. Now, let us start with the mean. Now, let us make also one other observation, that is, look at this. If you look at this, we have y bar which is a linear combination. So, y bar is a linear combination, it is a linear combination of h comma v bar, and therefore, since h comma v bar are Gaussian in nature, y bar is also Gaussian in nature, output vector y bar is also Gaussian in nature. Okay. Since h comma v bar are Gaussian, output y bar is also Gaussian, all right. So, basically we have an output vector y bar which is Gaussian, parameter h which is Gaussian. So, we have a Gaussian scenario. So, now we can use the principle of Gaussian MMSE parameter estimation. Okay. So, we can use the principle of MMSE estimation for Gaussian parameters. So, y bar is Gaussian, this is an important aspect, h bar is Gaussian. So, basically since both of these are Gaussian, we can use Gaussian MMSE result for Gaussian MMSE estimator, where the parameter y bar, where the observation vector y bar and the parameter h are both Gaussian. Okay. So, towards this end, first let us find the mean of the observation vector y bar. Well, what is this? This is the mean of y bar equals x bar h plus v bar, which is equal to x bar into expected value of h plus expected value of v bar. Well, expected value of v bar, this is equal to 0, since the noise is 0 mean. We have said that expected value of h, the unknown channel coefficient, is mu h. So, therefore, this will be equal to x bar times mu of h. So, this is expected value of y bar. We can also represent this as mu bar y, which is basically, by the way, since y is an n cross 1 vector, mu bar y is also an n cross 1 vector. Therefore, let us rewrite this clearly, mu y bar equals x bar times mu of h. Okay. So, this is an important result. What is this? This is the mean of the observation vector y. Mean of observation, mean of the observation vector y bar. Okay. So, we have an expression for the mean of the observation vector y bar, that is mu y bar, and we know that the expression of the Gaussian MMSE estimate, we know that the expression of the Gaussian MMSE estimate is given as h hat is equal to r h y into r y y inverse times y minus mu bar y plus mu h, where r y y is the covariance matrix of y, r h y is the cross covariance between the parameter h and the observation vector y. Okay. So, let us also write that down. We know that the MMSE estimate h hat equals r h y into r y y into y bar minus mu y plus mu h. Okay. R y y, this is the covariance of y or covariance matrix rather. This is the covariance matrix of y, this is the cross covariance of h comma y bar. This is the MMSE estimate of the channel coefficient h. Now, what is r y y? Remember r y y, the definition of r y y equals expected value of y bar, minus mu bar y times y bar minus mu bar y transpose. This is the definition of r y y, which is the covariance matrix of y. This is equal to, now let us substitute for both y bar. Of course, we know y bar equals x bar times h plus v bar minus mu y bar equals x bar times mu h times the transpose of this quantity x bar times h plus v bar minus x bar into mu h transpose. Okay. And this is equal to, now this can be again just write it in this fashion, which will help us to simplify x bar into h minus mu h, just remove the mean of h, that is mu h from h plus v bar. Now, you can see times x bar into the same thing mu h plus v bar transpose. Okay. Now, we are going to make another assumption, which is also a very intuitive assumption. We are going to assume that the noise v bar and the parameter h are uncorrelated, because the parameter is the channel we are trying to estimate, the noise is the noise at the receiver. So, naturally these two will be independent in fact, alright. So, we are going to assume that these two quantities are uncorrelated. I mean, since h is Gaussian, v bar is also Gaussian, uncorrelated will also mean that they are independent anyway, because h and v bar are Gaussian in this particular scenario. Okay. So, we are going to make the assumption that expected value of h minus mu h times v bar transpose equal to expected value of v bar into h minus mu h is equal to 0. This basically implies that noise and parameter in this case are independent, or let us simply write that they are uncorrelated, because this simply implies that they are uncorrelated, but since they are Gaussian, this also translates into independence of h comma v bar. Okay. Now, therefore, I can simplify this expression, for r y y as, I can write it as the product of the terms expected value of expected value of the first term will be x bar transpose times h minus mu h square, since h is a scalar quantity, plus of course, we can look at the other terms. These are going to be expected value of v bar times h minus mu h into x bar. We are going to simplify this later, since x bar is a constant quantity, constant pilot vector, which will therefore come out of the bracket. So, this will be expected value of well, this is x bar transpose v bar h bar, and this is expected value of x v bar transpose into h minus mu h. Just write each term carefully, x bar plus expected value of, well, v bar transpose. Just now again, since x bar is a constant vector, I am going to simplify this. Since x bar is a constant pilot, we have x bar is a constant pilot vector, therefore, this is equal to expected x bar transpose expected value of h minus mu h square. We know this is equal to sigma h square plus expected value of v bar into h minus mu h into x bar transpose. We know this is equal to 0. We just said that the noise and the parameter are uncorrelated, okay, plus expected value of x bar v bar transpose into, or expected value of x bar into h minus mu h into v bar transpose. We know this is also 0 once again, because the noise and parameter are uncorrelated, and the last term is v bar transpose. We know this is sigma square times identity. This is the covariance matrix of noise. This is the covariance matrix of noise. This is the covariance matrix of noise. Therefore, the net, this expression can be simplified as sigma square times x bar transpose plus, or sigma h square times x bar transpose plus sigma square times identity. This is the expression for the covariance matrix of the observation vector y bar, that is r y bar r y y equals sigma h square times x bar transpose plus sigma square times the identity matrix. Similarly, now I can also simplify the expression for r h y, the cross covariance between h and y bar, that will be given as r h y equals expected value of, well, h minus mu h into y bar minus mu y bar transpose, which is basically, I can simplify this as h minus mu h times, writing this below, this will be, we already simplify this, x bar into h minus mu h plus v bar transpose, which will be equal to, well, x bar, once again taking x bar out of the bracket, x bar times expected value of h minus mu h whole square plus expected value of h minus mu h into v bar transpose. Of course, we know this is equal to 0 because the noise and parameter are uncorrelated, and this, remember once again, is simply expected value of mu h minus mu h square, this is equal to sigma h square. So, therefore, this is equal to basically simply, well, this is simply equal to, well, there will be a transpose here, x bar transpose sigma h square x bar transpose, which is basically your r h y. Okay. So, this is basically your expression for R H y. In the above this we have derived the expression for R y y. Now, all we need to do is substitute it in this expression here for the MMSE estimate, substitute it in this expression for the MMSE estimate, and we are going to derive the final MMSE estimate. So, basically the final expression for the MMSE estimate is given as expression for the MMSE estimate H hat is expression for MMSE estimate of your channel coefficient H hat is H hat equals R H y, which is basically we have derived R H y, this is sigma h square x bar transpose times R y y inverse, which is sigma h square x bar transpose is sigma square times identity this inverse into y bar minus x bar into mu h plus mu h. And what is this? This is your R y y inverse and this is your R h y, and this is therefore your final expression for the MMSE estimate of, this is the final expression for MMSE estimate of, this is the final expression for MMSE estimate of channel coefficient H. This is the final expression for the MMSE estimate of the channel coefficient H. Alright. So, what we have done in this module is basically we have derived a succinct expression for the MMSE estimate of the channel coefficient H in terms of the observation vector pi y bar and the pilot vector x bar. Now, what we are going to do, of course, this expression is complicated, similar to the wireless sensor network scenario. Again, similar to the wireless sensor network scenario, we are going to simplify this expression and give a nice expression, a much more simpler and nicer expression, which has a lot of which makes sense intuitively, or which one can explain, and which yields a lot of interesting insight into the nature of this MMSE estimate. Alright. So, we will stop this module here and continue with the simplification in the next module. Thank you very much.